The date was March 1941. The Battle of the Atlantic was not merely a naval engagement. It was a cold, unforgiving mathematical equation, and the Allies were demonstrably losing it by every metric of material survival. The core of this grim formula was a single, vital variable: tonnage. To survive the mounting industrial demands of the war and simply keep its population fed, Great Britain required a relentless flow of 30 million tons of imported goods annually, a cascade of food, high-octane fuel, steel for tanks, and ammunition for its beleaguered armies. The German Kriegsmarine, led by the shrewd Admiral Karl Donitz, understood this existential logic perfectly. His dreaded wolf packs, coordinated groups of sleek, deadly U-boats, were not hunting warships. They were hunting the merchant vessels, the very arteries of the British Empire. They were sinking Allied merchant ships faster than the combined shipyards of the free world could possibly replace them. In this single catastrophic month alone, March 1941, over 500,000 tons of desperately needed shipping were sent to the bottom of the Atlantic, dragged down by the relentless force of German torpedoes. The strategic situation was beyond desperate. It was an industrial hemorrhage that threatened to bring the entire British war effort to its knees.
The British merchant fleet was bleeding out, its crews decimated, its schedules impossible to maintain. The grim analysts of the Royal Navy calculated with terrifying certainty that at the current, accelerating rate of attrition, Britain would face nationwide starvation and irreversible industrial collapse within a mere 6 months. The entire strategic situation depended on the island nation's ability to import, and its imports were vanishing beneath the waves. They needed ships, not the costly, complex, and time-consuming warships of the Royal Navy, but simple, utilitarian cargo ships. And they needed them in numbers that defied all known industrial reality. They required a 1,000-ton hammer to smash the German submarine calculus. In a desperate gamble, a small British delegation arrived in Washington, D.C., their faces etched with the strain of their country's plight, clutching a set of unlikely blueprints. They met with Admiral Henry S. Land, the stern and seasoned head of the U.S. Maritime Commission, the agency responsible for overseeing America's peacetime shipping production. What the British delegation placed on his desk was not a marvel of modern naval engineering, nor a cutting-edge design to rival the swift German U-boats. It was a ghost from the past, an almost comical relic of a bygone age.
The design was based almost exactly on the Dorrington Court, a standard British tramp steamer that had first sailed the seas in 1879. It was 441 feet long, slow, boxy, and possessed a silhouette that was unforgivably high. Crucially, it was powered by a 2,500 horsepower triple expansion steam engine, a reciprocating steam technology that had been effectively obsolete since the launch of the Titanic 30 years prior, having long been replaced by faster, more efficient steam turbines. The Americans, masters of modern, sleek engineering, were appalled. American shipbuilders, immensely proud of their modern turbine-powered C-class freighters, looked at the British plans and erupted in laughter, seeing it as an insult to American industrial progress. They immediately nicknamed the clumsy vessel an ugly duckling. Its defects were glaringly obvious to any naval architect. It was painfully slow, capable of a maximum speed of only 11 knots, making it a near sitting duck for U-boats that could surface and travel at 18 knots, easily overtaking their prey. It lacked the watertight compartmentalization essential for modern naval survivability. It was crude, heavy, difficult to handle in storms, and fundamentally archaic. Admiral Land himself, a staunch proponent of efficiency, was reportedly hesitant.
President Franklin D. Roosevelt, however, possessing the necessary vision and foresight, saw past the ship's ungainly appearance to the stark arithmetic of survival. Upon seeing the design, he famously remarked, "I think this ship will do us well," before adding almost under his breath, "She really is a dreadful-looking object." He understood that aesthetics were irrelevant. Volume was everything.
But the laughter in the shipyards, the sneering contempt for the boxy 19th-century design ignored the most critical, grim logistical reality of the moment. The United States did not possess the industrial capacity to build modern, high-pressure steam turbines in the numbers required for a mass cargo fleet. Every specialized gear-cutting machine in America, the handful of specialized tools required to manufacture the complex rotors and gears for modern turbines, was already booked solid for the next 2 years, dedicated solely to building the high-speed engines for the Navy's essential destroyers and cruisers. If the Allies wanted a cargo ship now, one that could be built in massive numbers to reverse the tonnage equation, it had to be this one. It had to be powered by the simple, low-tech, cast-iron triple expansion engine, a machine so basic that it could be manufactured by almost any foundry in the country, freeing up the specialized machinery for the fighting ships. This ugly duckling had to be simple enough to be built by masses of totally unskilled labor and robust enough to carry 10,000 deadweight tons of cargo, the equivalent of 300 medium tanks or 2.8 million rations of food. The order was given, bypassing the naval establishment's objections. The ugly duckling was officially designated the EC2S C1, a bureaucratic classification for an emergency cargo vessel. But the public, who would soon see these ships filling every port, would know it by a different name, one that spoke to its ultimate purpose, the Liberty Ship. To build these ships, the government turned to a man who had never constructed a single maritime vessel in his entire life, Henry J. Kaiser. Kaiser was not a shipbuilder. He was an industrialist of the American West, a giant who had built immense structures, the Hoover Dam, the Grand Coulee Dam, and hundreds of miles of modern roads. He viewed a ship not as a piece of nautical art or a complex naval vehicle, but simply as a structural steel project that happened to float. Kaiser secured massive contracts to build entirely new shipyards on the West Coast, in Richmond, California, and Portland, Oregon, designed from the ground up not for craftsmanship, but for relentless assembly line throughput. His approach was immediately, violently radical, a complete rejection of centuries of maritime tradition. Traditional shipbuilding was a craft, an artisanal trade. A keel was meticulously laid on the slipway, and then highly skilled shipwrights would build the vessel slowly, piece by piece, riveting hundreds of thousands of steel plates together. A noisy, painstaking process that required immense skill and specialization. It was slow, artisanal, and required years of apprenticeship. Kaiser didn't have years to spare. He didn't even have months. Kaiser's first and most crucial innovation was replacing the laborious traditional rivet with the far more efficient electric weld. Riveting a single seam required a specialized team of 4 skilled men, a heater to heat the rivet, a catcher to catch it, a holder-on to keep it in place, and a riveter to hammer it home. Welding, by contrast, required one person with a torch, turning shipbuilding from a 4-man, highly specialized team effort into a single operator manufacturing task. This change alone slashed labor hours and exponentially increased the potential speed of assembly.
But Kaiser's true revolution was prefabrication, the wholesale transfer of the construction site inland. He realized that the single immovable bottleneck to volume production was the precious slipway, the waterfront space where the ship was assembled and launched. If you insisted on building the ship entirely on the slipway, it tied up that valuable real estate for 6 to 12 months, limiting the yard's output to a handful of ships per year. So Kaiser stopped building ships on the slipways altogether. Instead, he transformed his shipyards into true assembly plants. Massive sections of the ship, the entire bow, the double-bottom hull, the deckhouse, the engine casing, were built in open lots adjacent to the water, or even in factories miles away. These sub-assemblies, some weighing over 100 tons, were meticulously constructed upside down or sideways to allow for downhand welding, which was easier, faster, and produced a stronger weld than the difficult, demanding process of welding overhead. Only when these massive Lego blocks were finished, painted, and often pre-wired, were they lifted by giant custom-built gantry cranes and dropped precisely onto the keel waiting on the slipway. The ship wasn't built there. It was merely joined together in a matter of days.
This modular industrial method solved the crippling labor crisis. All the existing skilled shipwrights were already working on Navy contracts building battleships and aircraft carriers. Kaiser hired everyone else who was willing to work. Farmers who understood machinery, shop clerks who understood detail, housewives who had never before held a tool heavier than a skillet, and African Americans who had migrated from the South, often facing intense discrimination but finding unprecedented opportunity. In 1941, the average shipyard worker was a white male with 10 years of experience. By 1943, the workforce was composed of a diverse array of new industrial workers, and at the Richmond shipyards alone, women famously made up 27% of the total labor pool. They weren't just helpers, fetching and carrying. They were the welders, the fitters, and the crane operators, sealing the hulls that would cross the U-boat-infested Atlantic. The ugly Duckling, the symbol of desperate necessity, was being built by the very people it was designed to protect, a true manifestation of the arsenal of democracy. When the first Liberty ship, the SS Patrick Henry, was eventually launched in September 1941, it had taken 244 days to build. It was a solid start, demonstrating that the design was viable, but it wasn't nearly fast enough to beat the U-boats. The German advantage was still growing. The Maritime Commission's initial build time goal was set at a build time of 6 months per ship, or 180 days.
Kaiser and his managers, fueled by competition and a sense of patriotic urgency, treated the production line like a competitive, high-stakes sport. They ruthlessly analyzed every movement, every weld, every crane lift, using time and motion studies that would have made Frederick Taylor blush. They standardized the plumbing, eliminating custom fits. They pre-installed the electrical wiring and machinery into the deckhouses before they were even lifted onto the ship, saving dozens of precious hours on the slipway. The production time began a staggering freefall. By January 1942, the average build time had fallen to 200 days. By July, through continuous refinement and process innovation, the average was exactly 100 days. By late 1942, the average time to build a Liberty ship, from the laying of the keel to the moment of launch, had stabilized at an incredible 42 days. The shipbuilders who had laughed were now stunned into silence. American yards were soon launching 3 Liberty ships every single day, a cascade of steel and steam that was mathematically breaking the Kriegsmarine strategic model. The Germans could sink a ship in minutes, a single flash of a torpedo, but they couldn't build a torpedo fast enough to match an entire nation's shipyards building a functional 10,000-ton freighter in a month and a half. But Henry Kaiser was not just an industrialist, he was a master showman and a shrewd propagandist. He wanted to prove that the limits of physics and logistics could be shattered completely, that the industrial miracle was not just an average, but a potential reality. He ordered the Richmond shipyard to attempt a highly publicized stunt that would make headlines around the world, sending a clear, unequivocal message to Hitler and Donitz. The target of this incredible feat was the SS Robert E. Peary. Work began at 12:01 a.m. on Sunday, November 8, 1942. The process was a masterpiece of coordination. The keel was laid in 60 seconds. By the time the sun rose, the bottom shell and inner bottom were complete and sealed. By Monday evening, the hull was rapidly taking shape, with massive sections being welded in place. By Tuesday, the complex 135-ton triple-expansion steam engine, that same obsolete design that was so easy to mass-produce, was lowered precisely into the engine casing. By Wednesday, the deckhouse was welded on, complete with the captain's clock already hanging on the wall and the pre-installed bunks waiting for the crew. On Thursday, the hull was painted and final rigging was installed. On Thursday, November 12, just 4 days, 15 hours, and 29 minutes after the keel was first laid, the SS Robert E. Peary was launched into the waters of the Pacific. It was a propaganda masterstroke that stunned the world and demoralized the Axis High Command. It proved beyond any doubt that American industry wasn't just waking up, it was operating at a velocity and scale that the Axis powers, bound by their insistence on technical perfection and artisanal manufacture, could not comprehend, let alone match. But speed and mass production came at a necessary and sometimes fatal cost. The archival precision of history requires us to look at the failures, too. The Liberty ships were built fast, but they were built with a hidden, fatal flaw, one that had nothing to do with German U-boats or torpedoes. On January 16, 1943, the SS Schenectady, a tanker built on the Liberty hull design, was sitting peacefully at the dock in Portland, Oregon. The water was calm. The crew was aboard. Suddenly, with a sound described as a colossal gunshot, the ship split in two at the dock. The bow and stern jackknifed violently into the water, a catastrophic failure that seemed impossible. It was immediately recognized as a crisis of the highest order. If the ships were breaking apart at the dock in calm waters, how could they possibly survive the violent, cold, and unpredictable storms of the North Atlantic?
The subsequent urgent investigation revealed a hidden enemy: brittle fracture. The type of steel used in the ships, combined with the extreme cold temperatures of the North Atlantic and the stresses concentrated around the square corners of the cargo hatches, became brittle. Unlike the old riveted ships, where a crack would typically stop when it reached the edge of a steel plate and a junction, a welded ship was essentially one continuous piece of steel. A crack starting in a hatch corner or near a pore weld could travel the entire length of the hull in seconds, snapping the vessel in half with terrifying speed. A brilliant metallurgist at Cambridge University, Constance Tipper, identified the core scientific problem: the specific grade of steel used in the mass production process became unstable and brittle below certain temperatures, a phenomenon known as the ductile to brittle transition. The ugly duckling had a literal glass jaw when exposed to cold water. The fix was logistical and practical rather than a full structural overhaul which would have slowed production fatally. They couldn't change the steel grade as production was too far along and the material too standardized. Instead, engineers developed crack arresters, simple, long steel straps that were laboriously riveted to the hull, ironically bringing riveting back into the mix, to interrupt a continuous weld seam and stop cracks from spreading.
The ships kept sailing because they had to. The risk of the ship snapping in half was statistically lower than the immediate existential risk of the German blockade starving Europe and crippling the Soviet Union. By the end of the war, the laughably obsolete, slow, and ugly Liberty ship had become the indispensable backbone of the greatest logistics operation in human history. American shipyards ultimately produced a mind-boggling total of 2,710 Liberty ships. They carried the crucial tanks that fought at El Alamein, the millions of tons of spam, wool, and ammunition to the Soviet Union through the icy Murmansk Run,
and they formed the essential core of the artificial harbors at D-Day. They were the constant, monotonous, inescapable tide of American material might. The average Liberty ship was designed to last only 5 years, a disposable ship for a disposable industrial war. Yet, their underlying simplicity and robust construction meant that many sailed for decades after the conflict ended, forming the basis of the modern global merchant marine that connected the post-war world. The Germans had better individual tanks. They had better submarines. They developed advanced technologies like jet engines and rockets. But they fundamentally miscalculated their war based on the speed of soldiers and the complexity of perfect machines. They forgot to calculate the exponential speed and overwhelming volume of the American assembly line. The Liberty ship proved a profound and final point in the industrial age. Technical perfection is the ultimate enemy of victory, when facing an enemy whose sheer volume can bury your finest creations. The shipbuilders laughed at the design, but the Liberty ship, the boxy, steam-powered symbol of emergency, got the last laugh, delivered in 10,000-ton shipments, relentlessly, every 42 days until the war was won. If you enjoyed this deep dive into the industrial precision of World War II, hit that subscribe button. Next week, we're uncovering the secret factory that built a B-24 bomber every 63 minutes. You don't want to miss it. This is the WW2 Archives.